I think we're going to be discussing the Navier-Stokes equations or in various topics around it for one today and one more lecture, okay? But we're going to discuss a little bit about some physical intuition first, like we were in the end of the last class, and in the later part of the class today, we will do a little more work, sort of more mathematical work with the Navier-Stokes equations to show you some of the analytical solutions that can be obtained, which in the previous class we just sort of glossed over. Okay, we'll go back to those, a couple of them, and show you actually how you can work them out. So we were discussing at the end of last class this sort of competition, if you will, between inertial and viscous effects. And I show you these two movies where you have here in the right you have this orange fluid where at the moment you start rotating the container, the whole fluid starts moving with it because it's dragged on by its own viscous forces. And so you have here the situation where the high viscosity of this fluid results in the viscous effects dominating the flow, and inertial effects somehow are negligible in comparison. In the left, let me perhaps go back and see if this works. I think they both start at the same time. The left one, the yellow one, you can see that once the container starts rotating, only a thin layer close to the wall is dragged, and the middle part of the fluid seems not to really move at all. It takes a while for that middle part of the fluid to start moving with the container. It has inertia. Inertia here is still dominating the flow in comparison to viscous effect. And here is another example that we have, two videos. So now, again, they will start rotating. So you see the one on the right is very viscous. The one on the left is not very viscous. They start rotating the container, and this little floating cherry or something doesn't really move very much. The one on the right moves, the whole thing moves together because it's dragged on by viscosity. And so in the left, the inertial effects are dominating. In the right, the viscous effects are dominating. And we were discussing that the Reynolds number indicates the competition between the two. In the case of very low Reynolds number, you obtain what is called creeping flow. A creeping flow is this situation where you have Reynolds number, which is, say, much smaller than 1. In this situation, viscous effects completely dominated. So recall that the Reynolds number is rho VL over mu, or also we can use VL over nu, the letter nu, the Greek letter nu, which we use for the basically just mu over rho for the fluid. So there's three ways to achieve a low Reynolds number, as you can see. One way would be to have a very low speed, clearly from the relationship with the Reynolds number. The second would be to have a very small length scale. And the third way to have a very large viscosity. So in the previous movie, we had a very viscous fluid with the little cherry thing floating, and the very large viscosity results in a very low Reynolds number, and we have a flow dominated by viscosity. Well, I don't know exactly what the Reynolds number might have been there. Perhaps it was larger than 1. It was low, a small Reynolds number, but perhaps it wasn't as small as what we use here to define creeping flow, which is Reynolds number smaller than 1, much smaller than 1. So that viscous effects really dominate completely. Yes?
Does that mean that you could zoom in as far as you want to in a turbulent flow and you would have a laminar flow?
If you have Reynolds number much less than 1, it's always going to be laminar. Always laminar. Stokes flow is always laminar. In fact, because of the fact that Reynolds number is much smaller than 1, you can actually say that all of the inertia effects are negligible and completely eliminate that. So basically, imagine that the Reynolds number is much smaller than 1 because the velocity is very small. In the Navier-Stokes equation, we have this nonlinear term that multiplies velocity with gradient of velocity, right? The derivative of the velocities. This second order term, if you will, if the velocity is tiny, very small, smaller than 1, you can neglect it. And so you get a simplified form of the equation, which is called the Stokes equation, which is linear. And in the absence of nonlinearity, the flow is going to be always in fact, you can get exact solutions, analytical solutions in many cases. In most cases you can. So it's always going to be laminar. So I've got a couple of examples here for a case with very low speed. Here in this photograph, which is a sort of color-enhanced satellite image of a glacier, is a situation where, despite the fact that this is a very large system, this is creeping flow because this velocity is so small. In fact, the velocity of a glacier is only a few meters per year. So really slow. And it's creeping flow. That's why we call it creeping flow. You get the sort of a... It's ice. Yeah, it's ice. Now this photograph is enhanced, color enhanced, but it's some satellite acquired image, and it's enhanced to show you some signatures of the motion that has been happening there of the glacier. Now here on the right is a little video that I found on YouTube of it's very fun. It's a white blood cell chasing a bacteria. And the little red ones must be red blood. The little round ones must be red blood cells, I suppose. Oh, you got it. You got it. So Stokes flow, for example, is a sort of branch of fluid dynamics where many of the biological phenomena that occur at this scale, this length scale that I was showing in this video, fall into this category. So the little vesicles flowing, and all of this little tiny phenomena are studied using Stokes flow, and you can see a lot of research also being published, people applying Stokes flow for that type of problems. And another application of Stokes flow perhaps is things at the micro scale, little small, for example, micro devices sometimes have a much smaller Reynolds number than 1, or they may have a Reynolds number of, the order of 5 or 10, and it's not really creeping flow, but it's still small Reynolds number, and it's still going to be laminar. So anything with low Reynolds numbers like that is going to be laminar. Creeping flow is either further down the range of Reynolds number of laminar flow. Laminar, 10, 100, it's going to be laminar, always. Yes?
What's considered a large flow?
Well, it depends on the flow, but we're going to discuss pipe flow as an example in a little while, because your second lab is on pipe flow. And for pipe flow, when you go beyond, say, 2,000, 4,000, more or less in that range, it gets turbulent. But if you're thinking about the laminar layer, the boundary layer around an airplane, then it's in the order of 100,000 to be really turbulent. And so it does depend on the geometry somewhat and the situation of the flow. And for each situation, people have observed experimentally when what we call transition to turbulence occurs. But anything in the order of thousands, it's, in the order of thousands and 10,000, we consider moderate Reynolds number, but in the pipe flow situation, it will be turbulent, even though it's a moderate sort of number. High Reynolds number, when people talk about, for example, simulation at high Reynolds number, they usually mean 100,000 millions. So for the case of Stokes flow, in fact, I want to give you a little bit of an idea of what, sort of results we can get mathematically. So suppose we're going to look at a very famous result for Stokes flow, which is the case of a sphere. So we consider a sphere of radius A, which is like imagine a grain of sand. This is one of the typical applications, a grain of sand which is settling in water, say. This is completely governed by Stokes flow because of the length scales. And we're going to assume steady state. And also we're going to neglect because it's creeping flow, then we neglect the convective term, convective acceleration, as I was explaining to Nathan a moment ago. We can neglect this nonlinear term because the velocity is very small. Basically, the inertial term is very small. And so the equation of motion in this case reduces to the weight components, the pressure components, and the viscous. And it's a linear partial differential equation because it's steady, and then we neglect the convective acceleration. All the acceleration terms are zero. Yes? So for the case of a sphere of radius A, it's convenient to use spherical coordinates. And if you recall, spherical coordinates I'm just going to sketch the derivation. I'm not going to do the whole thing. This picture is to remind you of spherical coordinates, where you want to go from the Cartesian x, y, z to coordinates which are a radius and the two angles which are shown in the picture. So this point over here would have coordinates r, theta, measured with respect to the z axis, and phi down here on the xy plane. And we can make a variable, a change of variable, where x equals to r sine theta cosine phi, y equals r sine theta sine phi, and z is equal to r cosine theta. And you can work this out, and I hope you've seen this before in your vector calculus or your engineering mathematics courses. So the Navier-Stokes equations can be rewritten in spherical coordinates for this particular simplified version of Stokes flow. This version of the Navier-Stokes equation, which is already simplified for Stokes flow, is this one. So basically, if you were to use your definitions of the divergence and the gradient and the Laplacian operators in spherical coordinates, you would have it. This is Stokes flow, the Stokes flow equation. And we also would have to have, for the case of the sphere, suppose the sphere, this is the case that we're looking at, suppose a sphere which is falling in a fluid with a velocity, a certain velocity, and the fluid, of course, goes around it, and so this is the situation that we're looking at, the fluid going around this sphere of radius A. And we do need some boundary conditions to integrate, to solve this problem in closed form. The boundary conditions are no slip, so the velocity, the theta component of velocity is equal to 0 at r equals a, and also r is equal to 0 at r equals to a. So we have no slip, and also well, this is no slip, and this is basically a no through, we call it, boundary condition. The flow cannot penetrate the particle. It's a solid particle. So the R component would be normal to the sphere, right? Normal to the little sand particle. So obviously it has to be 0 because the fluid cannot go through the wall. And we call this the no through boundary condition. The flow cannot penetrate that boundary. Then also we applied some sort of condition at infinity, that the velocity be unperturbed at infinity. And those are all our boundary conditions. R tends to infinity. And with this situation, we're not going to do it, but it leads to a closed form solution, which I'm just going to write down here. So you can get everything in closed form for the velocity in this case. You can get everything from the Navier-Stokes equation. You get UR is equal to, say, so suppose this is actually V0, the velocity of the particle falling here. V0, the steady velocity of the particle, or of the fluid around the particle, cosine theta times 1 minus 3a over 2r plus a cubed over 2r cubed, r being, of course, this r over here, the variable in the radial direction, and a being the actual radius of the particle, and mu theta, this is completely symmetric in the phi direction, but in the theta direction we have v0 sine theta minus 1 plus 3a over 4r plus a cubed over 4r cubed. And let me just give you a little pointer here that this equation here, if you look at the textbook by Post, there's a typo in the book. So don't be concerned if it doesn't match, because it's a typo. It's on page 176. Believe me, I checked with several sources. It's a typo in Post. So we have a complete result here for the velocity. Does this thing disappear? No. Okay, I have a movie. But to be clear of this result, maybe the green will look better. So we have, let's look at the very bad. We have r in this direction, and theta is in this direction, and phi would be sort of the angle on a plane perpendicular to the sketch, but the flow is going to be completely symmetrical around that. Okay, so we don't need to, it's kind of two-dimensional in that sense. And we have basically a flow approaching with V0, VO, V0, V0. And this is a very famous result. So the velocities, this is a very famous result. The velocities, just to be clear, are going to be VR in that direction and V theta in that direction. Just to be clear, those are the velocity components that we're talking about. Okay, it's a very famous result by Stokes. And there's some interesting things to say about it. Note that the velocities, which we find in closed form, are independent of the viscosity. For Stokes flow, this happens that, you get to a point where just things are moving so slow that just any viscosity is almost the same. They're all so big, basically. It's independent of the viscosity, and this is pretty much true of creeping flow. When you plot these, because you have a closed form solution, you can actually plot the velocities, you can plot streamlines. When you can plot the streamlines, you can see that there's complete symmetry of the streamlines. There's no wake. Symmetric in the sense, symmetric from the front and the back of the sphere are the same, so there's no wake. You know what I mean by wake? That little sort of disturbed part in the back of an object which is not streamlined. That's what we call the wake. So this one doesn't have a wake. And with the velocity ur and u theta, we can find the pressure. And everything is, I'm going to now clear these annotations to write down the expression for pressure, and finally the expression for the drag force, which is the most famous result for Stokes' drag, this drag around a small particle, which is, for example, a particle settling in air, or a small particle settling in some water. So it's a very standard, famous result, the force of drag in that situation, when the particle is moving at a terminal speed and a constant speed due to complete balance between the weight and the drag force of the fluid. Any questions so far? The remarkable thing about this situation is that you get a completely closed form solution with everything known out of the Navier-Stokes equations because of the fact that it's you've been able to simplify the equation for a steady case and Stokes flow, where the convective acceleration is also zero. So here is a video of the flow, how it would look like in this situation, visualized by some fluorescent dye in a situation with a very, very viscous fluid in the laboratory. And being an experiment is not precisely perfect, but you can see how the dye goes around the sphere, and behind this, it goes completely around the shape and does not form any wake behind it. This is the situation for Stokes flow. And we have UR and U theta. This is U theta known, so we can get the pressure from the back in the equation, and the result is P is equal to P0, the unperturbed atmospheric pressure, minus 3 mu A V0 over 2r squared, that's a 2, cosine theta. So this shows you that there is a pressure drag on the sphere, because P0 would be the free stream or unperturbed pressure, and you see that the pressure deviation is proportional to the viscosity, and is antisymmetric, being positive at the front and negative at the rear of the cylinder because of this here, right? So there's a positive deviation in the front of the cylinder's particle sphere, whatever it was, and a negative in the back. So this indicates that there is a drag force. On the sphere. The total drag is found by integrating some surface, the surface stresses, including both pressure and viscous stresses, Again, I'm not going to do the whole derivation, but I'm going to give you the answer, which is a very famous result due to Stokes. The total drag force is equal to 6 pi mu V0A. This is known as Stokes' law. Famous result for drag on a sphere obtained by Stokes in 1851. This force includes this pressure drag that we talked about, but also the viscous. Contributions. And now this form, this is for the case of, okay, so it is common practice to express drag forces in terms of a drag coefficient. We will, of course, discuss this at much more length later on in the course when we discuss flow, external flow around objects like, airfoils and so on. But you might be familiar with the concept of a coefficient of drag. Where basically you take the drag force and divide it by the dynamic pressure. Which is 1/2 rho V squared, V0 squared in this case, and by the area of the projected area of the in a plane normal to V0. This defines the drag coefficient, which is CD equal to force of drag divided by 1/2 rho V squared area. And if you put this back into this, you put this force in it, okay, you get, for Stokes flow, and this is again a very, let me put it in red because it's a very famous result, 24 over Reynolds number. So this is for Stokes flow of a sphere. You have this very neat result which gives you the coefficient of drag around the sphere. And this is very useful in many applications, like I was explaining, settling, and many environmental problems use settling speed. We can calculate the terminal speed based on this by doing a force balance between the weight of the particle and the force of drag, and you can get a terminal speed. It's called the settling speed. This is very useful in many applications, both industrially and environmental fluid mechanics. Yes?
So that total drag is 6 pi, that's only for a sphere?
Yes, for a sphere of radius A in a fluid of viscosity mu moving at a constant velocity of v0 in Stokes flow. So it has to be small enough A, small enough V, that the Reynolds number is much smaller than 1, or about 1. In fact, it turns out that people, this assumes that Reynolds is much smaller than 1, but experiments have shown that up to about 1, it still works. Yes?
What applications is this information useful?
For example, if you are calculating, suppose that there's some environmental issue that you want to calculate, how much time will it take for all of this say toxic particles to settle completely from the air so that we can wash the ground and use this space again, for example. Or you want to calculate how much residence time do I require for a industrial application where I want to settle all of the dirt in water for cleaning up the water. So first you want to settle the dirt, and then you want to take out all the clean water from the top to take it to some sort of disinfection stage afterwards. First you want to settle particles, or separation. In many chemical applications you want to separate particles from a liquid, and you just want to calculate the natural settling speed of that, and you want to make further calculations about how big the device has to be, all the objects have to be to allow that residence time, so all the things will settle down, things like that. Yeah.
Is that statement that total drag is found by integrated surface stress true in general, or is that only in Stokes flow?
The total drag is found by integrated surface stresses in general. In the case of Stokes flow, we can do it neatly and it gives you a result. In many other cases, we're left with an integral. We can't really. We can do it numerically if there's a general shape, and but it requires you to know the stresses and the pressures, because there's a contribution from both tangential and normal stresses, and sometimes you don't know that. So then you would have to do some sort of numerical calculation to obtain the pressure. So that's why you can get it from computational fluid dynamics. But for general cases, you can't really get a closed form solution, a neat little result like that. Yeah.
The pressure and the stress is the function of the U and the viscosity.
Yes, I've skipped the tangential stresses, but that's also going to depend on the viscosity. And you see that what's interesting here is that the normal pressure also has a viscosity component. The fluid is kind of so viscous that it kind of pushes on this thing. It doesn't go completely around like always tangential. So the normal stresses have a viscosity component. This is a strange or different thing. And so we were looking at the, let me just add that there's a terminal velocity that you can obtain. This is the last result. It didn't really fit on my slide, but I think, well, these actually are in the textbook, okay, these results. But again, I repeat, there's a typo there. No, they don't do the whole derivation. They do like me, like just tell you from here you get there, boom, result, you know. I think you wouldn't appreciate if I did the whole thing on the board step by step. We've done that already, and we did it for Navier-Stokes, we did it for Bernoulli. Those are the most important ones, and now we're going to, you know, I think that you believe these are well-established things, okay? 1851, so for exercise, you can do it one day if you're interested, but some of you are not. So suppose that the particle was actually falling by its own weight. Then you'd have the weight of the particle and a drag force, F of drag and weight. And because this is falling at a constant velocity, these must be in complete balance. And so that allows you to get a terminal velocity, or settling velocity, which is what's used, as I was explaining, in some of these applications. And the result is V, let's call it terminal, equals 2/9 a squared g over nu, rho s over rho, where rho s of the density of the sphere and rho is the density of the fluid. So this is a pretty neat result. You can calculate the velocity which is reached when the drag force and actually buoyancy are taken into account. Exactly balance the weight. Well, actually, buoyancy will point upwards, won't it? Drag plus buoyancy exactly balanced the weight. So, I think I have a little movie about this. Oh, this is the movie already. You've seen it. Okay. This is now let's close this chapter on creeping flow, and let's go back to the discussion about the importance of Reynolds number, which we started this whole discussion from. So you recall that I was saying that in the beginning of this discussion that there's a differentiation between laminar and turbulent flow, and I also said that the Reynolds number was very important. This number, Reynolds number, of course, is named after Mr. Reynolds. Actually, I think he became Sir at one point. He's British engineer with, I think he got a degree in mathematics from University of Cambridge, but he was really an engineer. And he got a position in the University of Manchester, where in fact he did his famous experiments. In the year 2009, it was the 125th anniversary of his famous experiment, where he developed this idea of this magical number that had all this meaning, and it's been hugely influential. It can't be stressed enough how influential this simple experiment had. So what he had was this sort of little bell-shaped entrance to a transparent pipe. This is actually his own sketch of his apparatus. And he had a transparent little pipe here, and he had this bottle over here was feeding a streak of dye into this pipe, so he could observe what was going on over here. And there's some sort of sump that accumulates what's going in there, okay? And so he injected dye into the pipe, basically the water was just falling by gravity into this sump. And he observed that at low velocities, and actually these are his actual sketches reproduced there. He observed that at low velocities, when he injected the dye, there was a filament which extended all the way to the end of the pipe. Now, if the water in the tank was not at rest, maybe this dye streak would move a little bit, but it sort of always remained more or less like a long streak. As the velocity increased, at some point in the tube, he observed that the dye would completely at once mix, like it's shown in the sketch in the middle. Now, he was very clever, and what he did is he used a electric spark to view this situation in the middle, like in an instant, and he could see that what he saw as a complete mixing of the dye and the pipe was actually a set of little eddies that turned around, and he could see that with a spark. So he made a lot of interesting observations, and he was able to see that this dimensionless group here, Reynolds number, we call it now, this dimensionless group, which he interpreted to be the ratio between inertia and viscous strain, like we still interpret it to be today, was very important and would distinguish between whether he got the situation at the top or the situation at the bottom. So, and if you read some of there's some you can find some reproductions of his original papers, and they're very sort of poetical in his observations. I have a little quote here that I like. Let me read it to you. And he said, this is a quote from his paper. The internal motion of water assumes one or other of two broadly distinguishable forms. Either the elements of the fluid follow one another along lines of motion which lead in the most direct manner to their destination, or they eddy about in sinuous paths the most indirect possible. This is the way that science writing was, 1850, basically poetic. We don't do that anymore. And I've put on Blackboard a paper that was published to celebrate the 125th anniversary of this famous work, and describes a bit of the history. It's not the only thing that Reynolds is known about. The actual paper that he published has another very important result, which we will discuss at another time. Here is a picture of the actual apparatus, which is today still at Manchester University. And here are some videos of what you would see if you repeated these experiments today. This is the sort of instantaneous picture of the little eddies, the sinuous motions that he talked about. And in the left you have a laminar flow, and in the right a turbulent flow. He found that he could see this laminar situation for Reynolds number less than about 2000, and the completely turbulent case for Reynolds greater than about 4000. But for Reynolds between 2000 and 4000, he saw that it could be either way. It depended on the atmospheric conditions and so on. So this is what we call the transition. At this point, between 2000 and 4000, the fluid is, just about to become turbulent, but not quite. Above 4000, it's definitely turbulent. And this is related to your lab number 2. So you will be repeating Reynolds' experiment and observing this in the lab very soon. Definitely before Thanksgiving. We're trying to find a way to be able to avoid your labs sort of encroaching on your study time for the final. And it's very hard indeed because it's a big class. And but so the TAs are trying to work out a way that you could have both labs before you go to the Thanksgiving holiday. So this is a very famous result. Oh, I've forgotten that we usually take a break. This is a good time to take a break. We're a little late, but I was thinking that you were tired. I was wondering what's that. Okay, 10-minute break.